In this paper, we introduce a novel volumetric homogenization approach for simulating knitwear. Firstly, we employ a rod-based yarn model to generate a detailed volume mesh. Then we lump the yarn level mass to the mesh's nodal points to isolate inertia. Next, we optimize the loss functions for homogenization. Finally, we obtain a volume mesh with specific material distribution, which significantly speeds up high-quality knitwear simulation compared to full-scale yarn-level simulation. Our first example is rib 1x1. We first show the yarn-level simulation results. Our method shows the high stretchability in the perpendicular direction, similar to the yarn-level simulation. Our method and HYLC both yield plausible results. The second example is stockinette. Yarn-level simulation results shows the curl at the edges for this knit pattern. Our methods successfully capture this behavior under stretch. HYLC performs well too, but our method is much faster for simulate this scene. The third example is draping the rib patch on a sphere. The yarn-level simulation exhibits inhomogeneous deformation at the fabric sphere contact region. Our method can capture this phenomenon. Without spatially varying material, HYLC cannot capture it. In this example, we stretch the basket weave patterns. Our method produces high-fidelity knit stretching results that are nearly identical to yarn-level simulation. Montague knit pattern example is not very periodic. Our homogenized mesh still capture the yarn-level dynamic very well. Flame knit pattern is a non-periodic yarn structure. We use 92,000 elements to successfully capture its behavior and simulate it at 8.5 fps. Our method accurately captures its bending behavior. In this example, we simulate a hanging fabric consisting of two patterns. Our method remains effective in this case. This combined pattern poses a challenge to classic homogenization theory. We hanging this fabric in another direction. We have 77,000 DOF on the mesh, and our simulation takes 121 milliseconds for one step, which is about 80 times faster than running the simulation at yarn level. We twist a square basket weave fabric. We can separate the processing of energy constraint and collision constraint so that the homogenized model interact like a yarn level model. While not exactly same as the yarn level simulation, our results are natural and realistic. Here we have some more complex experiments. There are 78,000 DOFs on this mesh, and our method runs at 3 fps for this example. Here we drop a puffer ball with 207,000 DOF on stockinette fabric. The homogenized mesh has 102,000 DOF. In these example, the mesh level simulation about 100 times faster than the yarn level simulation. We test our method on more full garment animations. Our homogenized material used 329,000 DOF in this example. With our efficient GPU PD simulator, the runtime performance is nearly 1.2 fps with 420,000 elements. Thank you for your attention.